Good morning, everyone. It's Friday, October 16th today, and let us start our lecture. So I recall we have 2 weeks before your second exam. It will be just in 2 weeks from now, October 30th on Friday. So take your time seriously and start preparing. I recall your homework 4 is due today. If you didn't, many of you have already submitted it. If you did not submit yet, please do it soon, as soon as possible, so we can post the solution soon. Take a little time, but submit it. And today we are going to start next chapter. It will be chapter 5. So please, it will be next. It will be chapter 5. We are starting today, and we will be talking about open systems. So I will post next homework related to chapter 5 very soon. I hope maybe we can do it this weekend or a little bit later. We should get approval from Dr. Mabain as well. And it will be due Wednesday, the week after next week. So you will have some time. And also maybe I will give you one more optional quiz before the exam so you can get prepared, maybe on Monday in a week from now. But key point that we are starting chapter 5, and you should conceptually see the difference between chapter 4 and chapter 5. So what is conceptual difference? And what we are going to do in chapter 5? In chapter, remember, and chapter 4, it was about closed system. Now we will be talking about open system. How we call it control volume. Remember, control volume means open system. So what is open system? Remember, open system means that our boundary is prepared in such a manner that we have holes. So mass can go in and out of your system, which is different from a closed system. So why it's so conceptually different and why it's so important? What you should really realize here. Because I tell you in advance, key mistake that you are going to do in your exam 2, key mistake that 10 or 20% of you will do, especially those who don't attend my lectures, it will be that you confuse what system it is, closed and open. And you will see why it's so crucial, because equations are different. Equations we talk about are fully different. Some students ask me, why don't we consider too many examples in the class? And one of the reasons was that so far we did not come to open system. You know, it is in this chapter that we are going to talk about nozzles, compressors, turbines, throttling valves, mixers, heaters, heat exchangers, other devices. So most devices we faced in our life, in our industry, in our environment are open systems. There are not too many closed systems. And so that's why so far we don't consider many examples. We talk about piston cylinder assemblies, rigid tank, something like this. Now we'll talk about open systems. So please realize the difference. And so what is conceptual difference? Now you may ask, why do we derive equations sometimes instead of posting it? Because when you derive equation, you really understand how it comes from, when it's applicable or not. So I recall how we end last lecture. So what was, you just finished chapter 4, you just finished homework number 4. What was the major equation in chapter 4? And I think you will say that, yes, some people say about boundary work, but the major equation was this one. The delta E is Q minus W, right? The delta E, the change of energy between two states is heat transfer minus work transfer, or Q over cycle is work over cycle, right? Will it be valid for open systems? And now you may remember not, because if you remember how we came to this equation. So this equation, which is nothing that first law was stated, how we come to this. It says that the energy cannot be conserved, it cannot be just transferred from one state to another. So if you have a closed system, we say the change of energy in such the system, it was heat transfer through the boundary minus work transfer over the boundary, right? And convention comes with sign minus here. So how we derive it? We talk about closed system here. Will it be valid for open system? No, it will not be valid. So that's what you should realize, that now for open system, it will be not this one. First law will look differently. So you cannot employ this equation anymore until I allow you. Forget about it. Now we should derive another equation for open system, which will account for mass transfer through boundary. Does it make sense for you? So key point of chapter 5, forget about chapter 4, forget about this equation. Chapter 5 will be a little bit more complicated. Okay? Okay. So that is our objectives for chapter 5. So we need to develop first law and employ it for control volumes for open system. We should see how this equation will look like. And we should see that what will be moving, and if you talk about open system, it means that something goes in and something goes out. It will be moving flow, okay? Moving flow. So we should know how to deal with this moving flow. What will be boundary work here? What will be heat transfer? What will be flow work? What will be kinetic and potential energy? So we should arrive to some counterpart of first law. And you will see, I tell you in advance, that key parameter in this chapter, it will be enthalpy. You already deal with enthalpy, right? It's U plus PV. You know why we introduce enthalpy. But now enthalpy will become your primary parameter because it's combination of internal energy and flow work. So actually first law will be balance of enthalpy. I will talk about it. Not entropy, enthalpy still. In next chapter, it will be entropy. Now we talk about enthalpy and this will be your key parameter. So what we are going to do? Now I will go through simple things. So first I will talk about something very silly, very trivial. But occasionally it will become harder and harder and it will be something very difficult. So please don't sleep and focus and listen to me. So we will talk about open system. So what is open system? It's something like this. You have a system with some inlet and some outlet. Well, I may have many outlets, many inlets. So I want to write balance equation of mass and balance equation of energy for it. And what I will say here, again, we say in this class that mass is conserved. Mass, in terms that mass cannot be destroyed or created, right? So, right, it's not nuclear physics, here mass is fixed. So we will say here the time rate of change of mass contained within control volume is what? It's rate of mass which comes in and rate of mass which comes out, right? Here it is. So I can write it like this. Do you understand this formula? What I write here? The dm over dt CV subscript CV means control volume. That's what we deal in this course. It will be m dot I minus me. Or everybody remembers what is m dot? It's mass flow rate. It's amount of mass propagating in and out through unit time. And remember, in typical physics, in typical engineering, we deal with flow rates. I told you that there is no reason, when you talk about moving flows, there is no reason to talk about mass of Monongahela River. But there is a reason to say how much water propagate per Morgantown per day or per any unit time. So that is m dot, mass per unit time in kilogram per second or whatever. So what I say here, it's very simple. So let's say, and typically if you're in person class, I would say like this. I will say how many students we have in the class. And you may say, okay, in the room we have like 70 people. Okay, and then I ask you, let's assume I want to monitor how many people I have in the class each second. What should I do? There are two options. One option that every instant I will just recount all of you. But there is something easier. What I can do? I know that I have 70 people in the class. I will see how many people comes in through one door and how many people goes out, right? And if I add people who came and eliminate people who moved out, I will always know how many people I have in the class. Yes? Does it make sense? Yes or no? Well, provided that nobody died during my lecture, luckily, and there are no, and provided that I don't kill anyone in the lecture, and provided that new students are not generated, that new student will not be born during my lecture, of course. But that's what we talk about mass. Mass is not generated or destroyed. So that's what we say. If you want to know how mass of your system changes, you should account what comes in and comes out. And of course, if you have many inlets, many outlets, it will be just summation over inlets and outlets. Does it make sense? So in this class, in this chapter, subscript I means inlet, okay? subscript E means exit. Sometimes we will use subscript O like out, in and out, in and exit. Is it trivial so far? Any question about this? This is differential form of this equation. Basically, and I recall what what are mass flow rates. That basically remember that what if you talk about one-dimensional flow, if you have pipe like this, that basically remember what is mass flow rate. It was in chapter 2. Mass flow rate, it's nothing but density by volumetric flow rate. It will be average velocity over cross-section area. Do you remember this formula? Right? And if I have one inlet, one outlet, yeah, you remember. Excellent. If you don't remember, back to chapter 2. Okay. And basically, you remember that if you have one inlet, one outlet, m dot will be conserved, while volume should not be conserved. And in fact, you make compression and expansion, right? It's another way to write down is like this. It will be A by V divided by specific volume. So far, it's trivial, I believe. Right? And definitely energy which is transferred, energy dot E dot, it will be m dot by specific energy. Now, well, again, that it is, and also if you remember volumetric flows rate, what we can say here. There is so-called Gaussian theorem or circulation theorem, which actually tell about the same. It tells that surface integral it can be coupled to volumetric integral, right? This is physically. Mathematically, it's much simpler. So mathematically, and by the way, it's good explanation if you take a fluid mechanics class. So if you take like advanced mathematics, sometimes they tell you that you can convert surface integral into volumetric and vice versa. But now you may see that what we say here is quite simple. So let's assume you have like bath like here with water, right? So, some water comes in and comes out. So what is our conservation of mass simply state? It simply stays, I believe it's trivial for any student, should be, if you know mathematics. So what you say here? What is left-hand side here? What is this integral? This integral stays. What is the change of mass per unit time of water in this bath? And what is this integral? This integral changes how much water propagates through boundaries, which means through tube and through exit, right? Plus and minus. And together, what? Together they give you 0 because mass cannot be destroyed or generated. So what we say here, you simply say that mass cannot be created or destroyed. So change of mass inside the system is what comes in minus what comes out. Exactly. Coming back to my example about students in the class, what I say here that change of my students in the class, it will be equal to number of students who drop my class, minus number who drop the class, plus people who enter the class belatedly, right? That it is. So basically that is your total formula, and we write like this. I may say that this is differential form, and this is integral form of conservation. Otherwise, in fluid mechanics also we call it continuity equation. Is it trivial? I believe so. I hope so. Now, so, well, now you should realize that there is transient flows and stationary flow. So what is stationary flow? Stationary flow actually means the following, that your flow does not change with time. It means that if you look at this bus, and if you look at this bus in 1 hour, it will look identically. It means that the same water comes in, the same water goes out. So for steady system, you should not have this term. This term should be 0. It means that it's steady. Okay. Otherwise, if this term is not 0, then your system is unsteady and it changes. And unsteady systems which depend on time, we call it transient. Transient means time dependent otherwise. So if you have transient system, you can take this equation, integrate it over time, and you will have like this. So I integrate this equation in time by dt, and I will come that mass of my system at time t minus mass of my system at time 0, it's like this. It's summation. Again, definitely if I have steady system, left-hand side will disappear. So I want to tell you that most of the systems we deal with are steady. Otherwise, they would explode. turbines, compressors, they should be steady because you have many iterations per time. If they would be unsteady, they would have overheated. So most likely we'll deal with steady systems, but not all the time. And in last problems of your homework, it will be systems which are not steady. Okay. So again, if I talk about steady system, what does it mean? It means that left-hand side here is 0, as I discussed with you. So we don't have this left term, which means that this will be my equation, mass balance. If I have many inlets, many outlets, I have like this. Right? Does it make sense? For example, if you have mass balance for a steady flow, classical example, if I have, let's say I have system like this. I have two, let's say it's classical mixer. Assume you take a shower and you have hot water and cold water and you want to balance them to make like reasonable temperature for you. So what will happen? Here is one flow with mass flow rate of 2 kilograms per second. And here is 3 kilograms per second, another flow rate. So you definitely understand that outlet will be 5 kilograms per second. It will be the summation. So what we say here, it's just mass balance. Because if what goes out, it should be equal to what goes in. Otherwise, if water will, if it's not steady, then amount of water inside will grow or disappear, and it will be unsteady. Does it make sense for you? I believe so. Finally, I recall, I already told about this 10 minutes ago, but I recall that don't confuse mass balance and volumetric balance. So basically, this is classical example. What I have here, it's air compressor. What is compressor? Compressor is a device in which you pressurized your flow, so its density increases or volume decreases. So this is classical example of air compressor. So let's see, I have mass flow rate of 2 kilograms per second. And initial volumetric flow rate is 1.4 meter cube per second. It goes in. Okay, what is density here? Density will be mass over volume, m dot over the v dot, right? Now, what will happen at the outlet? At the outlet, please realize that if I have system like this, in the outlet, m2 dot will be exactly the same. It will be still 2 kilograms per second. But volume v dot, volumetric flow rate, will be different, as it should be. Because I pressurize my flow, so mass is conserved, correct? Your mass here is conserved, so this mass is equal to this mass or the flow rate. But volumetric flow rates are different because compression happens. There is no conservation of volume because density is different. Rho2 and here you have Rho1, here you have Rho2. They are not equal. They are different. Okay, as it should. But if you have incompressible systems, what are incompressible systems? Like liquid water, for instance, then definitely volumetric or density will be the same. As long as density is constant, volume is also conserved. So for instance, if you go to a store and assume you bought 1 gallon of milk, for instance, right? On 1 gallon of juice. Juice is like liquid water or milk is like water. So 1 gallon of juice, if you today you drink half gallon, and tomorrow you drink half gallon, then you will empty your bottle, right? Because, and the same for gasoline, the same for any kind of liquid. So then it's additive because you have conservation of volume. But if you buy a balloon or some kind of vessel with gas, you know, gas occupies the entire volume. So if you buy 1 gallon of hydrogen and spend some amount of it, you will still have 1 gallon of hydrogen, right? Because it will occupy your volume. Because hydrogen is expanding, so mass will be conserved, volume will not be conserved, right? Is it trivial what I talk about? I hope. Another point, remember a concept about flow work or flow energy, how we call it, PV. So what is this term PV? I recall it again because sometimes it's really not easy to understand. I am explaining this term. So assume like now we are lucky if you want to drink water, you go to kitchen or bathroom, open the crane and you will have water there, right? Now, but somebody brings it into your home, right? There is pressure abundance in your pipes, in canalization system that, in piping system, in plumbing system that move it to your home. Imagine you don't have water in your home. What should you do? Then you should go somewhere outside to some kind of source of water, take a vessel of it and bring it home, right? And then you should take it out from home. So do you understand that you should produce some work for it? If I ask you, okay, here I have a vessel with 10 liters of water, please help me to move it out. Then we should take it and bring it out, right? Do you agree that we should produce some work to push it out? Do you agree that somebody produce work to bring it here? So now you may realize that when you open your crane and water flows there, that somebody did this work to bring it here. Do you agree? And this is what we call flow work. This is the work associated with moving flow. And this work is equal to PV. This is PV torque. It's important for us because it will form enthalpy. So now let's compare what we discussed before. So when you consider non-flowing fluid, when you consider fluid at rest, so remember what is mechanical energy it consists of. It's internal energy that we discussed, it's term U. Well, here we talk about specific values. They are small values, but if you multiply by mass, you will have total values. So this is internal energy. This is kinetic energy. Here we talk about specific kinetic energy. And this is potential energy, right? Remember chapter 2 we discussed it. So this is for non-flowing flow. Now, for moving flow, for flowing fluid, in fact, in addition to them, you will have flow energy or flow work, which is PV torque. So again, so please realize that on the one hand side, this is like related to the process, but on the other hand, it's a property because P is a property and V is a property. So if you multiply by mass, it will be capital PV term. Now it's small v term, right? So basically, this is, so please realize this value theta, it's mechanical energy associated with moving flow. So do you agree now that this value theta, what is this value theta is? It will be counterpart, it will be an analog of E for moving flow. Do you agree? That this is for flow at rest, this is for moving flow. So we have this term PV there. Do you understand? And now tell me, please, what happens if I will combine these two items, PV and U together? What is this? Remember? By definition, it's enthalpy, right? That's how we defined it. Specific enthalpy or total enthalpy in general case, right? Exactly, this is enthalpy. So, yeah, H capital or H small, whatever it is, right? This is H small. If you multiply by S with H capital. So, and I come to what? I come to this equation. Or like this. Or like this. Correct? So now, do you, if you compare first equation and third equation here, do you agree? Please, do you agree that enthalpy plays the same role for moving flow as U for flow at rest? Do you understand this and would you agree with this? H and U, okay? And if you realize it, do you agree now that H in chapter 5 will play the same role as U in chapter 4? Roughly speaking. Okay? So you almost ready. That was easy. Now you almost ready to something difficult. Now difficulty will start. Be prepared. Wake up. Okay. So that's what I say here. And so you realize E it's flow at it's E it's specific mechanical energy of flow at rest, and theta its counterpart for moving flow. Now, if I multiply both of them on m dot, what I will have? I will have this is will value for moving flow. This so actually energy of moving flow, it will be nothing. It will be what? It will be m dot by theta. It will be this term. This is amount of energy transport, and this is amount of energy transport per unit time. And I recall again that we mostly talk about second equation because no reason to talk about. If I ask you what is energy of Monongahela River, you don't know what I mean by energy. But if I ask you what energy of this water, if you have like a hydropower plant, and what is the energy generated by this power plant per unit time, what is its power, then it makes sense to calculate. It will be m dot multiplied by c. Do you understand this? Please ask me something. And also you will realize in this course, and I will tell in advance, that very often term h will be higher than these two terms. Very often we will neglect kinetic energy and potential energy. And now I want to tell you something that I will repeat it many times, but that there is one more really classical mistake that many of you may do. So here we have three terms here, right? Specific kinetic energy, specific potential, specific enthalpy. What are units of this value? Where do you typically take units for this? What is the units for enthalpy? Where do it will be kilojoule per kilogram, right? If you open tables, you will see that your enthalpy, it will be what? It will be kilojoule, correct? Per kilogram, okay? Kilojoule per kilogram, okay? Now, if you consider this value, what will be value for velocity? Meter per second. So when I take it squared, it will be what? It will be meter squared per second squared, right? And if I calculate GZ, it will be, again, remember G, it's Newton per kilogram by meter, it will be again, it will be, if you convert it, it will be actually joule per kilogram. If you multiply by mass, it will be mgz, it will be joules. So what I want to tell you here, please realize that meter squared over second squared indeed equal to joule per kilogram. But it's not equal to kilojoule per kilogram. Okay? Kilojoule per kilogram, it will be what? It will be 1,000 meters squared over second squared. So that's what you should account. 3 orders of magnitude. Enthalpy is big term. You may realize that if you have 20 kilojoule per kilogram, it's 20,000 joule per kilogram. So it's 20,000 meters squared over second squared. When we come to more examples, you will realize it. This mistake will be done by 25% of you, unless you pay attention to it. Take it seriously. And how to avoid mistakes, I tell you many times, always write down units. Always write down dimensions. Don't just put numbers. Then you will never confuse. If you have kilojoule plus joule, you will realize that something goes wrong. But if you have 10 plus 20, you will confuse, right? Imagine I have 3 boxes of cherries plus 5 cherries. How much I have together? I have 3 boxes plus 5 cherries, which is about 3 boxes. But if you forgot about boxes, you will say 3 plus 5, you will have 8 cherries or 8 boxes. Don't do this mistake. Anyway, so any question until this? So what I'm going to do next? Next, I am going to show and derive first law of thermodynamics for open systems, okay? Energy conservation for open system, for a system with moving flow. Very similar like you did for closed system, but with other terms now. So to do it, I will talk about energy balance, energy rate balance. So what will be here? Let's say I have my system. This is my control volume. This is my inlet. This is my outlet. And we realize here that mechanical energy, what goes in and out is here, right? So now I will say that what is the rate of change of energy in the system? It will be heat transfer through the boundaries, right? Minus work done by the system, work transfer. And up to this point, I'm still exactly up to this point like we were in chapter 4. But also, so we have this term. So if I don't have this term, do you agree that up to now I am in line with chapter 4? What happened so far, it was chapter 4, right? But now we have this term. So we will have mass transfer. So let me write this down. So I will write now the d over dt is equal to q minus work. And what I write here? Plus mass energy transfer through mass in the inlet minus mass transfer through out. Do you agree with this? Again, up to this point, I'm in chapter 4, right? Or chapter 2. So what I wrote in the right now, it's exactly what we had in chapter 4. But in general case, we have mass flow rate. So now you may see that in fact what I'm deriving, it's not something fully new. I extend previous equations. So equations that I will derive now, it will be valid for closed system as well. Because what is closed system? Closed system will mean that there is no mass transfer. So if there is no mass transfer, I don't have this term. What will happen if there is no mass transfer? If there is no mass transfer, there is no this term, there is no this term. I will come back to a closed system. Okay? But now we have these terms. We have mass transfer, and these terms will actually dominate. They will be actually stronger than expected. Okay? So these terms, m dot terms, will actually major terms in chapter 5. Please realize and don't confuse. Okay, what I do next? Now I have, so what are my terms here? I have, let me see here. What is here? I have this term and I have this term, correct? Do you agree that I can get it from this expression? Right? That I'm going to do. So, in fact, it will be like this. Please ask me something. Do you understand this equation? Look at this. So, do you understand that if system, what will happen with my equation if system is closed? Do you understand that if my equation is, my system is closed, that these last terms in the equation will go out? If my system is closed, then what? If my system is closed, again, I'm here, I'm in chapter 4. But if my system is open, as it should be, then I do have these terms, and these terms, they do dominate over heat and work transfer. They are my major terms. They are big terms. Do you see? Okay. Now, yeah, questions, please? Yeah. Yeah, that makes sense. Excellent. But that's important. So, and that's what you shouldn't confuse. Now you may realize that if you forgot about this term, you fully confuse your problem and will never solve it, right? Now, let's proceed. So that is my equation that I rewrite it here. Let me call it equation 1. Now, let me say something else. So basically, this is what we have. But now let me ask you, so what is W here? What is Q? Q is heat transfer, but what is W? In fact, you will realize that W here, it's not just work done. It will be work done inside my system, by work done by inflow and work done by outflow. Do you see? So in fact, I do have these two terms here. I have these terms. I have this term. I have this term and I have this term, right? What are these terms? These terms show flow work. That I told you. We are lucky in 21st century that you can drink water, you can get water from crane at your home. Imagine that you should go to a river to pick it. Then you will really realize how heavy you are. So pressure jump, your pump, our city provides this work for you, but these terms are here. So generally speaking, work here contains work inside the system plus work transfer in and out through mass. So what happened if I take this equation and substitute it here? Will you see what happened? Let's discuss it. This is work in and work out. So if I substitute here, that's what I will have. Do you see that my equation can be rewritten like this? So if I substitute, my term PV will come here. Do you see it? And what I can write now, if I see, basically what I wrote here, what is E plus PV? It's what we call theta terms. And my E term, it's U plus V squared of 2 plus GC. So please take a look. On this equation and this, it's exactly the same equation. So what do we see here? Take a look. What I say here, that my change of energy inside my control volume per unit time is what? It's my Q dot CV, which is heat transfer rate per unit time, minus work done inside my system, by system or on the system inside it. You see the difference? Now, this is my term CV. It's different from this term because here it was general work. Here it's work done inside the system. And what else I have? I have this term. When I have what? I have E plus PV, right? And what these terms mean? Do you recognize that it will be what we call theta terms before, right? These terms are theta, which corresponds to flow, moving flow, E plus PV. Remember how we introduced? And why I say this? Because remember that for theta, enthalpy plays a role of internal energy. So you know what I'm going to do next? Next, I'm going to combine this term and this. And what will happen if I combine this term and this? I will come to what? I will come to enthalpy. You see? Exactly, enthalpy, excellent. So let's do it. So basically here is my equation. Let me rewrite it like this. Again, why I'm deriving this? It's not because I want you to remember derivations, because I want you to understand how equations come from. And when you understand, you will never use it for a closed system. Believe me that when you see this, you will never use for a closed system because you will understand that V is what comes in. So what I have here? I just rewrote this equation like this, and now this terms U plus PV forms enthalpy. So that is what I have. So in fact, now I have exactly the same equation, but now in terms of thetas, in terms of enthalpy. So here is my equation. If I have many exits, I will have just summation, and I will have like this. So equation at the bottom that you see, this is your major equation for this chapter. So please take a look and ask me questions. So equations that you see at the bottom in the frame, d over dt is q minus work in this, all equations that, let me write it like this. So this equation, it's your major equation for chapter 5. Do you understand all terms here? Do you understand what we are talking about? I hope so. Please take a look at this equation. And please, let's think together what it means actually. Like I say, it actually means balance of theta terms because we talk about moving flow. So what you see here, again, I recall, if I don't have mass transfer, if my system is closed, what does it mean? It means that m dot is 0. Do you understand? So it would mean that these terms will go out. So if these terms will go out, what do you see? You see exactly the same equation like in previous chapter. Okay? So what does it mean? It means that this equation that you see here, general equation, in fact, this is not like first law for open system. This is a general form of first law of thermodynamics. It describes any system, closed or open. If system is closed, it's like this. Okay? Do you understand this? If your system is closed, it's like this. If your system is open, it's like this. This is your basic equation. So now, when you will start solving any problem in chapter 5 and later, write down this equation, and you will see what to do. That is your major equation. And you will see that in major cases, your mass flow terms dominate over heat and work transfer. So it will be like this. Do you understand this? Now, luckily, you are still students and you solve simplified problems. So most likely, in the next couple of weeks, you will solve the problems which are simplified. So you will not have these terms, all of these terms in your equation. So I read your text body. Very often, and most of the time, it will be stated that your system is steady. So what does it mean that it's steady? It means that I don't have this term. This term will be 0, okay? Maybe it will be stated that you have insulated turbine, insulated system. Insulated means it's or just stated adiabatic, no heat transfer. What does it mean? It will mean that this term is 0. If you have nozzle or diffuser, if you don't have compression or expansion, you will not have boundary work. It will not be this term. Very often you will be neglecting kinetic and potential energy because that is not something you need in this course. It will be like this. But generally, you consider the entire equation. And now you may ask me a very good question. You will ask me, okay, so which terms I should account, which not? And you know it's a difficult question. I cannot tell you for sure for all cases. I will tell you like this. We will particularly consider different devices, and for which each device I will tell you what is the purpose of this device and what you should account, what you may waive. But if in the text body it will be stated about some terms, you should account. Like if it's stated that you have inflow with given velocity, you should account for it, and so on. But that will be your basic equation. And now I tell you the following. Let's assume that I have steady system. So what is steady system? Steady system is left-hand side is 0. Most likely you will have it like this. So what does it mean for us? If I have steady system, it means that left-hand side will not be 0. So what will happen then? Before talking about this, let's first consider transient system. So if I have transient system, then my left-hand side is not 0. So then I will integrate like this, and this will be my general equations that I consider. So if my system is not steady, then if you neglect kinetic and potential energy, this will be your general equation. This will be your balance between U and H. It will be like this. And one of the problems will be like this in your home. But if your left-hand side is 0, if your system is steady, then what? Then do you agree that you come to this equation that you see on the screen? Well, let me ask you, where is energy in this equation? Where is U in this equation? You don't see. You don't see, but it's there, right? There is known, but somewhere it is. Yeah, very good point. So basically, what is conservation concerned here? It's actually enthalpy balance. Do you see that if I have steady flow, it is enthalpy that you deal with. It is enthalpy table you play around, U plus PV. So that's, I recall in chapter 5, we deal with enthalpy. It will be enthalpy balance equation. It will be enthalpy analysis, how I can call it. Do you understand? Now, please remember what enthalpy is. Again, enthalpy, it's a combination of U plus PV. It's not energy. Energy exists in reality. Internal energy, it's really something that you have in your body you release. Enthalpy does not exist in reality. Enthalpy is some term which helps you to solve the problem that you take in your table. So it's not conserved. It can be generated or destroyed. There may be source of enthalpy. But so this is not conservation of enthalpy, it's balance of enthalpy, but it helps you to solve the problem. I tell a good example, like adjustable gross income. When you file tax return or when you apply for, I don't know, if for some benefits or whatever, what is required? All governments, all agencies, they require, or like insurance companies, they require write down your adjustable gross income, correct? And based on this, they calculate your taxes, they calculate some benefits, they calculate premiums and all of the things. Realize, adjustable gross income, it's not something that you ever see. It's some formula. You never have adjustable gross income in your pocket. You never deal with it. In your pocket or on your bank account, you have something different. Okay? But adjustable gross income, it's something to help, which helps the government, the agencies to solve the problem. So they use formula for adjustable gross income. They treat you based on your adjustable gross income, even you don't feel it yourself. So the same here. Thermodynamics treat your system based on enthalpy. Even enthalpy is just a mathematical combination. Do you understand this? So that it is. So that for steady flow, this will be your basic equation. Now, well, sometimes your problem will be simplified. So for instance, if you have one inlet, one outlet, then you may realize that instead of summation of this, you will simply have that m dot, m1 dot will be m2 dot, will be m dot, it will be constant. And you know the formula for it, right? It will be rho VA. So then your equation will be like this, and you can easily calculate. If you divide by mass dot, you will have these terms. And now it's nice to see that basically, when you look at the right-hand side of this equation, you have H, V, and G, they actually show specific values. So remember specific values, so what we have here. And the left-hand side in the numerators, you have energies like heat and work transfer per unit time. On the bottom, you have mass per unit time. So when you scale them, you will have per kilogram values, and you get out timing from your problem. So basically now your problem is steady. Now time is not involved in your consideration. Do you understand this? If you have steady system, if you look at it now, if you look at it during a day, and if you look in 100 years, it will be described by the same equation. System does not change. Inlet and outlet will change, but system does not change. Okay. Now, so what we will consider, and will be conceptual difference now. So one point. So what you should realize. So instead of simple, what you should realize now, instead of your simple equation, how it look like, instead of you will have this equation, right? Okay. Now there is one more point here to realize, especially for a steady system. So remember chapter 4. What was the difference between chapter 4 and chapter 3? Remember? I told you. It was like this. In chapter 3, we talk, and for your exam, we talk about state, right? We talk about one state that you identify from the tables. And now in chapter 4, we deal with sequence of states. We talk about the process. You have initial state and final state, right? And for example, what we consider? If I just talk about example in chapter 4. So for instance, you had what? You had some kind of piston cylinder assembly. So that was, for instance, you had system like this. That was your state 1, right? And then it was expanded and heated, and that is what was your state 2, right? And you can see the state 1, state 2, and the process between state 1 and state 2, correct? For the entire system. What will be now? Now it will be different for steady systems. So in this diagram, what is your state 1 and state 2? Please realize that here, your state 1 is your inlet. Your state 2 is your outlet for the same system. So consider yourself like a bird or fish which comes in. So let's say I have some kind of fish here, or bird or whatever. It comes in here, okay? It comes in. And that is initial state 1 inlet state of this bird. And then in the system, something happened. It will be boiled, it will be compressed, it will be cut, it will be tortured, it will be compressed, it will be evaporated, something will happen. And finally, this bird or what remnant of it will goes out. And this will be your state 2. Does it make sense? So when you look at the system, you realize there is inlet and outlet. Your state outlet, so what is steady system? Definitely at state 2, at outlet, your bird will look fully different from your inlet. Here it's alive and fresh, here it will be baked and dead. But at the inlet, you have another bird that flies, that coming in. And in that point of view, that's how your system looks steady. So for steady system, you may realize that locally in space, properties change. This property, this property, this property, this property, this property, they all different. But if you look at the inlet now and tomorrow, it will be the same. And if you look at the outlet today and tomorrow, it will be the same. So in property at state 1 and property at state 2 will be the same. Let me explain it like this. Look again let's look at Monongahela River, for instance. And here we have that, and it flows from Morgantown to Pittsburgh. okay, for instance. And let's consider fish which crowd of fish which go continuously along the river, right? So if you go to a bank of the river every day, so what you will see? You come in Morgantown to a bank of the river and you see some fish flow, right? Tomorrow you will look and fish still flow. And the day after tomorrow they still flow. In 1 week they still flow. So what does it mean that the river is steady? It will mean that every day you come to see it, you will see the same picture. Every day you come to see on Morgantown Bank, you will see the same river. And if you have a friend who will go in Pittsburgh to see on it, he or she will see exactly the same today, tomorrow, and whatever, right? So your viewpoint, your vision will be the same, and his vision will be the same, right? It means that your river is steady. But if you look at the system in terms of a fish which swims, definitely something is changing. Today this fish swim in Morgantown, tomorrow this fish swim in Pittsburgh, and Pittsburgh is something different from Morgantown, correct? Because inlet state and out state are different. System is steady, but inlet and outlet are different. Do you understand? Again, it makes difference from chapter 4. For chapter 4, state 1 and state 2 was for the entire system. Now state 1 is for inlet, state 2 is for outlet. Do you understand this? That is your balance. Again, mass will be conserved. Volume may or may not be conserved. It will depend. Do you understand this? Okay, please ask me some questions that we discussed. And what we are going to do actually next, and the rest of this section, we will talk about particular devices that we will consider. In general, we have to talk about a very complicated device, but we will talk about nozzles, diffusers, turbines, compressor, heat exchanger, mixers, throttling valve, and you will see how this equation look like. What terms you can neglect, what terms you will be counting, and that's most important. So that's what you should remember from here. You remember how we derive this equation. That is your major equation. All the time, write down this equation and see what terms to use. Okay, I will stop at this point. Please ask questions. Do you have questions? I recall, okay, maybe somebody wrote. So if you need to find. Yeah, exactly. If you look at the chart, exactly it is. If system is steady, right, yes, we're dealing with one parameter through another. Exactly, yes. DE over DT means that your system is steady. If it's not steady, then this final term and you should integrate. Most of the system will be steady, that you will consider. So what you should remember from today and from this portion, that basically what you should remember, that open system is conceptually different from the closed system. First law for open system look as follows, as we derived. It's extension of what we had before. Equation that we used in chapter 4 is just part of it, it does not work anymore. Inlet and outlet now are for the same system, and so state 1 and state 2 now coexist. Again, you will solve the same problem as before. If you know state 1, you don't know state 2 yet, you should go to tables and solve it from the very beginning. But now state 2 and state 1 coexist in space, in time, right? It's not like initial and final, they coexist. For a fish which swims through a chamber, it takes time, but now they coexist. Okay, and basically they coexist because for observers they coexist. Observer always see fish in the inlet and outlet. And also you will see that this is actually enthalpy balance. Anyway, I hope it was a good lecture. I will stop at this point. Take it seriously. This is some basics for chapter 5. Please don't, it will be more difficult than chapter 4, so take it seriously. I will stop at this point. Okay. And I will stop recording. Good luck.